So I'm Elliott Slaughter. I'm going to talk about Regent and Pygion. So I figured that it's been long enough since I gave this talk the last time that I should probably give everyone a refresher on what exactly these things are. And so so what I'm talking about sort of broadly, if you back up a little bit, is sort of how do you program Legion? And there's actually a bunch of ways to do that. I'm not going to talk about all of them today. But I thought that I'd just start with sort of a mental framework for like how do you organize these things? Like we've got tons and tons and tons of ways to program Legion. How do you actually think about how to use them? So I think, broadly speaking, there are sort of two general categories of interfaces that we have. There are the what I call direct interfaces to Legion. So I'm thinking C++. We actually have a Fortran API. Regent and Pygion go into that category. And then we have what I'm going to call the indirect interfaces, and I just made this up yesterday, so maybe we need some better terminology around this, but this is sort of all of the domain-specific ways you can program it. So Legate, FlexFlow, Flexi, and so on. So when I talk about a direct interface, I mean something that like directly represents the Legion programming model itself. So it has some notion of tasks, regions, partitions, like all the things, like when we give a Legion tutorial, like all those concepts are directly represented in some way. And in these indirect interfaces, like maybe there are some of those concepts as well, but they usually also have some domain-specific pieces. And so that means like when you're programming these things in the direct models, you have to think in terms of the Legion programming model. Like maybe there's some nice syntax on top of it. It might have some optimizations and some type checking and some usability features or whatever, but you still have to think about like I have some computation, I split it up in some way, I have some data, I split it up in some other way, I match between these things. And in the domain-specific models, usually, I mean the details vary obviously, but there's some sort of automation of that most of the time. So there's maybe ways of creating data structures, but maybe you don't need to think about partitioning yourself, or there are sort of improvements that those give you. So in these direct interfaces, it's sort of one-to-one with Legion. In the indirect interfaces, there's some mapping from whatever they're doing into Legion, with maybe a fallback, right? So some of these models also provide their own interfaces, but most of the time, the goal is to keep you higher level than Legion itself. So the direct interfaces are good for people who need control. The indirect interfaces are good for people who are focusing on the absolute ease of use above everything else. And maybe some additional effort is required when you want to get that control back. Okay, so today I'm going to talk about the direct interfaces. So there are actually going to be a number of talks about the various indirect interfaces. I think all of these systems are going to be represented in one way or another today. But I'm going to go through the direct interfaces. So to remind everyone, we've sort of got three major ones. There's the C++ API itself. So Legion is written in C++. It's exposed in a number of ways. C is also Fortran, but it's like any of the ways that you like program. People who do, go through this. Then there is Regent, which is a programming language. So all of the concepts of Legion are directly represented as features in the language, and that comes with a bunch of benefits. And then Pygion is sort of the same thing vaguely in Python. And being Python, we don't necessarily get quite as pretty of a syntax, but it does sort of vaguely the same thing. And so these come with different capabilities, like the metaprogramming differs. I don't know that necessarily matters to everyone here, but if you're in C++, you get templates. If you're in Regent, we metaprogram through Lua, and that means that if you want to have a loop, you actually get to write for something. You don't have to figure out the hideous syntax for looping in templates. If you're in any of these direct interfaces, we have dynamic checks for all the rules. So Legion is a system. You have to follow certain rules. We do dynamically check those things for you, but there's no static checking. And so C++ isn't, you get the C++ type system. It checks certain things, but it's not really expressive enough to capture all the things Legion cares about per se. Whereas if you're in these other models, then there's more checking for that. Obviously, if you're in Python, it's still dynamic, right? Because Python just doesn't do anything statically. But that is one of the things you get with these other models. The code is a lot more verbose in C++. And really, it's not so much that it's verbose, it's more that you have to build all the abstractions yourself, right? Legion as an API is not necessarily designed for you to just take it straight and write all the code. I have a code slide, on my next slide, so you'll see, what I mean. But what it means is you're basically responsible for doing all that yourself. And there is a certain way you have to write that code. So Legion has an idiomatic style. There is a certain way you do things in order to get performance. Mike mentioned one of those in his talk. So index launches are sort of like one of the key points when you're thinking about Legion code. And so when you're writing that code yourself, you just have to know all those things and you have to do them. Whereas in Regent, that's pretty much automatic. There are certainly ways to mess it up. But as Mike mentioned, it's a whole lot less common, and it's usually a lot easier to fix once you notice that something's gone wrong. If you're writing code to GPUs, if you're in C++, you're basically on your own. That means you can do pretty much whatever you want. So you can do CUDA, you can do Cocos, you can do Thrust, or whatever it is these days that NVIDIA people are pushing. But you're on your own. You do what you want. It works as well as what you set up for yourself. If you're in Regent, you get automatic GPU code generation, so that's nice. And if you're in Python, then there's this sort of, you get access to the Python ecosystem. So that has, a whole bunch of things, and it does whatever it does. Python's great for some stuff and maybe less great for other stuff. So the one thing to maybe keep in mind is if you're writing a code and you need access to absolutely bleeding edge features of Legion, there is a lag time for these other interfaces to get those. And so, one of the advantages of C++ is you do get access to those features right away. Whereas if we're in Regent, then there is a delay. Okay, so here's my code sample slide. This is an index launch in C++. Isn't that pretty? So, obviously, you don't need to read all this, but there's just a lot of stuff you need to do if you're in C++. Whereas if you're in Regent, you write a for loop, you're done. That's it. There's nothing else to know. And similarly, if you're writing GPU code, here's, a Saxby example, which is not actually that complicated, but it's still a lot of code to write. And if you're in Regent, you sort of stick this one line at the top that says demand CUDA, and you write the rest of your code. It sort of works normally. There is, the compiler is only so smart. It can do data parallel-ish things usually. And so there is some point at which, it won't be able to do your code for you, but at least for the simple things, it can handle it. Okay, so I'm going to talk a little bit about Regent today, and I just want to remind people about sort of what the stack actually looks like. So in case you forgot this since last time, we have the whole ecosystem for Regent is embedded in a programming language called Lua, which is a scripting language. And the exact details of that don't particularly matter. But the main thing to know is that when you're in Regent, we compile down to a programming language called Terra, which is essentially a metaprogramming layer that we use, and Terra lowers to LVM. So whenever we're talking about GPU code generation or high performance, code generation of any kind, all of this stuff eventually goes through LVM, and then we have Legion and all the rest of that stuff under that. Okay, so this is actually the first year I've had a Terra update because there is actually stuff to talk about. So we have recently, so in the last 2 years, we've had 4-ish LLVM updates. So we've done a pretty good job of keeping up to date with LLVM. So I haven't gone in and done LLVM 19 yet, but we had, the 4 previous versions. And we did get the SPIR-V backend for Intel GPU support, so that was nice. So that's sort of one of the key features that we need to extend the GPU support for Regent. And then we've got a whole bunch of other stuff. So we have RAII, we have allocators, smart pointers, concepts, ranges, and other stuff. And these are all basically due to 2 guys, Renee and Torsten, who essentially came along of their own accord and started adding a bunch of stuff. So this is, so there's a lot of great work here. So that's, stuff that you should check out. So in terms of, Terra's been around for a while. It's been doing a lot of great stuff. But this really extends the language to handle a whole bunch of new use cases. It won't all automatically work in Regent, so I'll just warn you about that. So there's some thinking that needs to go into sort of what do we pull into Regent and how do we do that. But it's good that we're actually like making progress in this because for a while the only update that I would give here is the new LLVM versions that we supported, which was not a whole lot of stuff. So I'll just briefly talk about one of those features. So RAII is an initialism for resource allocation is initialization. It's sort of a common programming pattern popularized by C++. So if you've ever done C++, you probably know this. If you think about the classic pattern with constructors and destructors and copy constructors and so on. So this is sort of vaguely equivalent to that. The semantics might be a little bit surprising to you. If you're used to C++, we don't quite have constructors. So the role of an initializer is to initialize an empty instance. It is not actually a constructor. And if you want to actually, if you're doing an assignment, then you run your copy constructor. And if you're doing an initialization, you initialize and then do the copy constructor. So that it works a little bit differently, but it's sort of vaguely comparable to what you would get in C++ 03. There's some thinking about how to do moves and things like that. We don't actually have R value references in the language, and so that is sort of a whole thing there. But this is moving forwards in terms of like being able to automatically work with data and not working at sort of a C level of abstraction with all the things we're doing. Okay, so that is work in progress. It's not quite landed yet, but hopefully that'll land soon, and then we'll be able to move on with other great stuff in the Terra language. Okay, so in Regent, I went through and I sort of made the laundry list of all the new things. I won't actually read them all to you, but this is all mostly I'd say sort of quality of life improvements. Nothing that is really sort of dramatically groundbreaking, except that we did finally remove static control replication because the dynamic control replication in Legion landed and is good enough for all the stuff that we've needed to do. There will be a talk on an FFT library that we have in Regent that's going to come up later today. One thing that I'll mention, we've had some of these features on this list for a while. So if you want features in Regent, come talk to me because all of these things get prioritized based on what you tell me. And if no one's complaining about it, it will not happen. So if you actually want these features, come talk to me and we'll figure out how to do that. But I'll talk about a couple of things that are new or new-ish in Regent. So one of the fun things about Regent is we can do a bunch of optimizations for you. And Mike showed on his slide how we do some of the predication stuff. So it sort of requires rewriting your code. You don't get to actually use an if statement in the generated code. You sort of have to launch your task and stick this predicate thing on the side. The nice thing is Regent handles this for you automatically. And that was actually true the last time I gave this talk. But what was not true is that it actually handles a whole bunch of other patterns. So like if you do an assignment into a variable, we handle the crazy code compilation to make that work. And so you can assign to something inside an if statement, and it just predicates, and it just magically works. And actually, that works for constants. It works for expressions. It could be, x equals y plus z. That works. We can make that happen. And the other thing that we can do is if you have nested predication, then we can chain the predicates together, and we handle all this stuff to make this sort of thing work. And so that's sort of an example of how the compiler understands your code. You write an if statement, but it knows that what you really want is predicated execution. It can do all of that for you. In terms of supporting hardware, so one of the new things that we got recently was support for ROCm 6.0, which sounds like it shouldn't be that difficult until you realize like how many moving pieces there actually are in the compilation stack. And so, in the process, this sort of flow diagram at the bottom is showing how we do it now. And so we have, again, we have Regent generates to Terra, generates to LVM. LVM spits out AMD GPU code. in the AMD GPU ecosystem, that's not enough. You can't just take that code and use it. There's this whole pipeline you have to go through to get that done the rest of the way. And the thing that we found, that was sort of tricky is that there are two tools you need to run through, Clang Offload Bundler and LLD, which is a linker, in order to get your final thing that you can finally actually load into the GPU. We had previously tried to use AMD's version. So AMD has their own fork. It is wildly broken. We cannot even compile against it. It is so broken. But I had previously thought, at least we'll use the tools that are available because these are external binaries. We'll just sort of use the things that are there. And basically, the short version is no, that doesn't work. You should just give up on AMD's LLVM completely. And the only piece that we're relying on from AMD now is the bitcode libraries. So if you think about math functions that are included, so your sine and your cosine and your whatever, right, optimized functions for your GPU, we read some LLVM bitcode from AMD in order to provide those functions. And so far, cross your fingers, it works. With a vanilla LLVM, I'm not sure that's going to continue working. And so this is probably something that we may need to revisit in the future. But at least at the moment, the story here is, if you use just the standard LLVM distribution and it is new enough, then we're okay. It needs to be exactly LLVM 18, exactly LLVM 18. Like no other version works, period. So that's just sort of one thing to keep in mind. But the good part about this is we have a major application called S3D, which is a direct numerical simulation of turbulent combustion. We've been working with these people for a long time now. I won't quote exactly how long because it's been long enough I probably won't get the number right. But we've been running on all sorts of machines on NVIDIA and AMD, and we ran on Frontier actually out to 8,000 nodes. This graph goes out to about 2,000, but we've done out to the full machine. And so this is work that was enabled by all of the optimizations that Regent does. And there will be, I believe, other Regent applications that you'll hear about later on, but I won't go through all of those right now. Okay, so in Pygion, what's new since 2 years ago? Well, we improved the interop with Regent, and that's about it. So, it's stable, it works, it supports major use cases, and it's been used in production. We do finally have a website. I realized in the presentation I gave at SC that we did not have a website. So that was pretty embarrassing. So I finally went around and actually did that. But it basically works, and there's not a whole lot to say because we've been doing production science with it. So here's a code we developed during the exascale computing project at Slack. This is a code for single particle imaging. So you've got, we have an X-ray diffraction or an X-ray laser. It shoots your particle, you get diffraction images out the other side, and we're trying to do a 3D reconstruction. And the trouble with this problem is the thing that is on your particle, you have no idea what orientation it's in, right? It's a protein or virus or what have you. But you're getting these images and you don't really know what you're looking at. And so the magic of this is sort of figuring out how to stitch these all together despite not having a whole lot of information about what exactly you're doing. And in this code, we took a kitchen sink design to building it. So we tried very hard not to rewrite anything ourselves. So if it existed and it worked, then we used it. So we ended up using NumPy, CubePy, Numba. We had some handwritten CUDA code for a handful of things that didn't exist, and some third-party CUDA libraries with Pygion as the task orchestration layer. And that worked well enough. There were some glitches when we moved to Frontier because it turned out not all those libraries were actually available for Frontier. So that was sort of an issue. But Pygion was not. So Pygion actually worked out of the box. It did exactly what it said it was going to do. And I don't think we actually hit any issues with it at all. And so we ran, this is going out to 4,000 GPUs on Frontier, and that pretty much just worked. And so I think, the success story as far as Pygion's concerned is that, all of this stuff did basically what it was supposed to do. And that's it for my update. It sounds like we're moving along, and so I think we'll save questions.